Okay, next we are moving to the need for biasing from load line lecture number 2. So in this particular case, we are going to discuss about the need of biasing, different type of biasing techniques as well as AC load line. So we'll see need for biasing. You know, a particular transistor can be operated in the normal operation. We should require two things. Already we know that the first one is a forward bias emitter base junction, you know that means input junction, and the reverse bias as a output junction. The output junction is collector base junction. These two should be satisfied, then only the particular transistor operating in the normal operation, like as a transistor act as an amplifier. Transistor act as a amplifier. Okay, now we'll see if it is not, the biasing not properly done, what will happen. If biasing not not properly done, we are facing the two effects. The first effect is a work inefficiently if not biased properly. The second thing is produce the distortion in the output. So why it is happened? Because if you are not properly biased, the Q point, that is a Q point, already we discussed in the load line, the Q point going to be shifted. So along with the DC line, the Q point shifted, the output going to be distorted. The output going to be distorted, that is nothing but that particular operation, the working are inefficiently. So completely we are not using that particular transistor. That's why we are going to provide the biasing techniques. So we have a different factors to affect the bias variations. So those factors we'll see. From the thermal runaway concept, I'm going to take one formula. You know that IB is equal to beta into IB plus ICO, right? So from that, IB beta into IB, okay, from that beta into IB plus 1 plus beta into ICO. Okay, this is about the formula. From that, what are the variable quantities here? Beta, IB and ICO. These are the variable quantities. To vary these quantities with temperature. So I maintain the collector current is constant. It is a possible to maintain the output cannot be destroyed. Q point going to be stable. So but we are increasing the temperature, indirectly increasing the IC, thermal runaway concept. So according to the thermal runaway, if you are increasing the temperature, what will happen? The leakage current going to be increases. This leakage current increases. Indirectly 1 plus beta, as well as IC current going to be increases. IC current going to be increases. You know that IC is equal to beta into IB. Indirectly, IC increases, IB increases. If IB increases, again the total entire result going to be affected to the IC. So this will be happened. Whenever power, that is a heat again generated, that heat again increases the IC. That is a regeneration. Just now I explained in the lecture number 1 thermal runaway concept. I don't want to repeat once again in depth. These are the effect. So how to overcome it? That is our now. We are providing 4 different biasing techniques. So first one is a fixed bias. Second one is a base bias with emitter feedback, third one is a base bias with collector feedback, fourth one is a voltage divider bias. We are going to discuss all these four. In the examination point of view, definitely will get one question from you. So before that, we are going to I'm going to give the stability factor. Stability factor, it is represented by S. Okay, I will give the stability factor definition. It is defined as the rate of change of IC with respect to ICO, right? So when both beta and IB are constants, so finally S is equal to rate of change, that is a DIC by DICO. This is a actually stability factor. Okay, so previously we have a formula from the thermal runaway. IC is equal to beta into IB plus 1 plus beta into ICO, right? So I'm going to derive this particular relation with IC differentiation. Derivative of IC by IC 1. Next, this is a beta into IB derivation. Beta is a constant, IB divided by DIC, right? Plus 1 plus beta is a constant here, DICO divided by DIC. You know that DIC by DICO is a S. I can replace here with respect to S. So finally, this is a S. S is equal to 1 plus beta divided by 1 minus this total entire thing, beta divided by IB divided by DIC. This is a formula for stability factor. Is it okay? Now you got the stability factor formula, as well as we know the different biasing techniques we are going to see. So before that, beta sensitivity also I'm going to provide beta sensitivity. So we'll see beta sensitivity. So beta sensitivity is represented by KB, that will be equivalent to beta by IC into DIC by DIB. This is for beta sensitivity. So we are going to discuss each and every case, these two formulas for each and every bias. So once again, I will provide two important concepts here. Stability factor, that is a beta for common base and common emitter configurations. So first one, common base circuit. In the common base circuit, IC is equal to, alpha into IE plus ICO, right? So from that you want stability factor S, that is a S is equal to DIC by DICO. That means that I can differentiate total entire thing with respect to ICO. So that means that derivative of constant, this total entire thing is a constant with respect to ICO, it is 0. Derivative of ICO is a 1. Finally, what is the S value for common base? It is a 1. In the examination, it is a chance is there. Stability factor for common base circuit, it is a 1. Okay. Next, second one, common emitter circuit. In the common emitter circuit, emitter terminal is a common for both input and output. In that particular case, IC is equal to beta into IB plus 1 plus beta into ICO. Again, differentiation both DICO, that is nothing but a S, stability factor. So from that it is 0 and then 1 plus beta. So finally stability factor S is equal to 1 plus beta. If it is beta is 100, what is this? 101. So that means that what is mean by 101? IC value changes 101 times with as much of ICO changes. That is about stability factor. Got my point? Right. Then we are moving to the different methods of biasing techniques. So first biasing technique is base bias. Okay. Different methods for transistor biasing. The first method is a base bias. Otherwise it is called as a fixed bias. Next, second one. Base bias with emitter feedback. Third one, base bias with collector feedback. Collector feedback. Fourth one, voltage divider bias. Okay, these are the biasing techniques. Why I'm applying the biasing technique? You need to fix the point Q, Q point, operating point of a transistor to stabilize without shifting when our temperature is variation. Due to the stability to maintain throughout our working in the practical condition, we are applying these biasing conditions. Okay, let us see one by one. Base bias. So base bias means, look at here, you see base bias. So base bias is a simple, just we discussed in the previous class in the before the load line. This is a RC, just feedback, base resistance here connected, feedback to the collector. Okay, it is grounded. This is a RB, this is a RC, this is a VCE, this is a voltage is VBE. Okay, this is a circuit for fixed bias. So base resistance connected to the collector, directly it is connected to VCC, right? So in the fixed bias condition, I will give some important formulas to you to remember that fixed bias condition. Those formulas are VCC. VCC is equal to, this VCC is equal to IB RB plus VBE. IB RE plus VBE. That is for VCC. As well as VCE. You want VCE. VCE is equal to VCC minus ICRC. ICRC is a formula. So in case of fixed bias, the beta and KB values are important. They will ask the question from the beta and KB. So the K beta value is 1 and stability factor is a 1 in case of base bias technique. So you should remember this point, that is enough for the base bias. In case of base bias, what we do, the base resistance connected to the collector, directly connected to VCC. In that particular case, stability factor is equal to 1 and beta sensitivity K beta is equal to 1. Then we are moving to the emitter bias, base bias with emitter feedback. So this is a base bias with emitter feedback. Just one modification here. Emitter resistance connected, RE resistance connected in the emitter circuit. So here base bias is provided. Along with that, we are connected RE into the emitter circuit. In that particular case, first we are going to discuss about the like IC current, IC saturated. When we'll get the IC saturated, VCE is equal to 0. In that particular case, I am going to calculate IC sat. So IC saturation is equal to VCC divided by, whenever VC is equal to 0, both are VC is equal to 0, nothing but short circuited. RN and RE are series, RL plus RE. This is about the saturation. Next, second thing we are going to find out. Next we are going to find out, just go through this particular VCC through IB through RE, then we are going to find out the VCC value. So from that, VCC minus IBRB minus IERE is equal to 0. Just apply the throughout here KVL. So from that, VCC is equal to IBRB plus VBE plus IERE. Okay, we have forgot this VBE. This VBE is a minus VBE. Okay, so so finally, IB is equal to IC by beta, you know that, and IE approximately equivalent to IC. If you are applying a substitute in both the cases, you will get VCC is equal to IC into RB by beta plus VBE plus IC into RE. So finally this is the formula for VCC. So therefore IC is equal to VCC minus VBE divided by RE plus RB divided by beta. So that is approximately equivalent to VCC divided by RE plus RB by RE plus RB by beta. Okay, then it is a actual procedure to find out this particular formula, but it is not required. Already I gave the beta rule to you to find out directly about IC value. How the beta rule will be, just I am going to explain here. Beta rule, this particular formula directly you can write it according to the beta rule, because in the examination don't want to remember all these things, directly you can now write the formula. IC is equal to VCC minus what are the voltage here, VBE divided by this base circuit RB is there, plus this is a RE. I am referred to the base circuit, that is a multiply with 1 plus beta, approximately beta. So beta into RE. Okay, total entire circuit referred to, for example, RE side. This particular referred to RE side. RE plus, if your beta resistance referred to RE side, so that is a RB divided by beta. Okay, this is a RE rule. Same formula or not? Yes, same formula. VC divided by RE plus RB by beta. That is to find out the IC. In the same formula, you can also write it as IC is equal to VCC minus VBE divided by RB plus, if you are referred RE in the base side, beta into RE. That is a 1 plus beta also you can consider. Otherwise 1 is neglected, beta into RE. So these are the formulas we have. So these already you know from the beta rule. Okay, if you are perfect in the beta rule, we can do any formula directly without doing all these calculations. Everyone clear? Finally, what we need to remember in the examination point of view, these are the formulas, beta rule formulas. Then we are moving to the direct questions, questions related to the this type of question in the 2018 question paper. It is there. For the circuit shown in the figure, find the IC sat and IC, VC, VE and VCE and K beta. Okay. First of all, I'm giving the values of K beta. Everyone note on the K beta formula also. So K beta formula, we'll write it here. K beta is equal to 1 divided by 1 plus beta RE divided by RB. This is the formula for K beta. Okay. I will write properly. Very important formula. K beta is equal to 1 by 1 plus beta RE divided by RB. So look at the particular problem. First of all, they are asking about the IC set. Whenever saturation occur, VC is equal to 0, just now I mentioned. Whenever VC is equal to 0, it is a short circuited, right? So that means that IC is equal to VCC divided by RL plus RE. RL plus RE. That will be equivalent to VCC is equal to 30 divided by RS plus RE. So 2K plus 1K. Okay. That value is equal to 10 milliamperes. All of you got my point? Right. Next, I want the current of IC. Just now I mentioned how to remember the formula. So how to find out the IC? IC can across this particular case. I can refer the base circuit into emitter. So VCC divided by RB plus RE emitter resistance plus this RB referred to the base. That means that RB divided by beta. Okay. So beta, that particular one important shortcut, base is moving to the emitter side or base is moving to the collector side, always it is divided by any resistance to base side, it is multiplication. So it is a 30 divided by RE value RE value is of 1K plus RB is a 300K divided by beta is 100. It is given. So beta, this is 100 beta. So from that, what is the IC value? 7.5 milliamperes. This is a maximum current, saturation current. This is the actual Q operating point, IC value current, if you are operating the particular case transistor. So that is a 7 milliamperes. After that, what they are asking, third one, this is the first bit, this is the second bit. Third bit is a IC. IC is done, VC. So VC is equal to VC is nothing but a voltage across this particular terminal. VCC minus RL into IC. VCC minus RL into IC into RL. What is the VCC? 30. IC 7.5 into 10 power minus 3 into 2K. It will be equivalent to 7.5 volt. Okay. At the second case, so fourth point is a VE. VE is nothing but here. So voltage across this particular resistance. It is a simple, VE is equal to IE into RE. You know that IE approximately equivalent to IC, we can make it. That means that IC into RE, that will be equivalent to 7.5. IE value is 7.5 milliamperes into RE is a 1K, that will be equivalent to 7.5 volt. Here not 7.5, just calculate, you will get 15 volt. Okay, VC is completed, VE is completed. At VCE they are asking. Next fifth point is a VCE. So VCE is nothing but a VC minus VE. What is a VCE got? 15. VCE 7.5. That will equal to 7.5. So KB, last one KB, K beta is equal to sensitivity factor 1 divided by 1 plus beta, you know the formula, beta into 1 by beta, that will be equivalent to 0.75. You know the formula for that. That formula will be 1 divided by 1 plus beta into RE by RB. Okay, so using that formula I did that. So finally you got some clear cut idea about the how to find out the solutions. Clear? Next we are moving to the next one is a base bias with collector feedback. See here base resistance is connected, and then this feedback is connected to the collector, not directly VCC. It is connected near to the collector point. We are leaving the RL load. Okay, this is call it as a base bias with collector feedback. In this particular case, we will going to discuss about the formulas. IC saturation is equal to VCC divided by IC saturation is nothing but it is 0. It is shorted. RL plus there is no RE, only RL. This is for saturation. Next, what about the VCC formula? This is the first one. VCC is equal to VC. I am talking about VC first. VC is equal to VCC minus this particular current is combination of IC plus IB. IC current plus IB current is a load current. So IC plus IB into RL. This is about the what we call VC. So if you are neglecting the base current, so finally VCC is equal to IC into RL. If your IB is neglected, base is neglected. Another way we can find out this particular VC is equal to IB RB. This is the combination IB RB plus VBE. IB RB plus into IB RB plus VBE. That is also another way. For example, this is the 1, this is the 2. I am going to equate both. I am going to equate the both. 1 is equivalent to 2. Then you will get IB RB plus VBE is equal to VCC minus IC RL. So if you am IB is equal to IC by beta, IC divided by beta, I can substitute. So finally IC by beta into RB plus VBE is equal to VCC minus IC into RL. So finally you want IC is equal to VCC minus VBE divided by RL plus RB divided by beta. Okay, if you are neglecting this particular VBE, finally VCC divided by RL plus RB by beta. So this is the formula for IC, but how to remember in the examination this particular formula, we'll see. So beta rule, using beta rule you can directly remember that particular formula. IC is equal to this particular IC we want to find out, that is a VCC divided by, if here they mention VBE minus VBE divided by, we are going through RL plus this base resistance. I can refer to the base resistance referred to collector terminal. So base resistance to refer to collector terminal, that is a RB divided by beta. Base resistance referred to emitter also RB by beta. Base resistance referred to in the IC collector terminal also RB by beta if you are neglecting one. So from that, this is the formula, can compare with this formula, yes or no? So without doing all these calculations, we can remember that beta rule, we can do the particular base bias with collector circuit, collector feedback. But you may get the sir directly give the formula, why you are doing all this nonsense? Because once I give directly this particular formula, you may thought that sir, why are we can see the notebook of textbook or any other thing, we can by heart the formulas, right? In the examination, it may get chance to forget the formulas. That's why I will give the concept to you. We can apply this concept in the examination. You can do play with the circuit within 1 minute. You can do the solution, no issue, because they will ask you only one parameter. They won't ask 5-6 parameters at a time. They will provide the one circuit. They will ask any one parameter in that. If you know every parameter formulas, we can do any problem is given, any bit is given in the examination, we can do. Okay. Next we are moving to the one problem related to that. Okay, before going to the problem, I will give the formula to you. KB, you should remember this particular formula. KB is equal to 1 divided by 1 plus beta into RL divided by RB. Okay, that is also you can do that 1 minus IC divided by IC sat. That is also the same thing. If you forgot this particular thing, we can apply this particular formula. So now we are look at the problem. In the shown in the figure, VCC is a 12 volt and VB is a 0.7, RL is a 1K and RB is a 100K, beta is a 100. Find IC is equal to, they are asking about IC, collector current, VCC minus, the formula, VCC minus VBE, because it is mentioned VBE, divided by, RB we are considered, okay, RB we are considered referred to the, what we call referred to the base, so RL plus RB divided by beta. So VCC is at 12 minus 0.7 divided by RL is a 1K plus RB is a 100K divided by beta value is a 100. So that will be equivalent to the 5.65 milliamperes. All of it clear? Next, second thing, what they are asking, VCE. VCE is equal to VCC, that is a 12 minus IC into IC plus IB into RL. Okay, so it is a value got IC 5 point, we neglect the IB value, 5.65 into RL is equal to 1 kilo. It is a milli. It will be equivalent to 6.35 volt if you are neglecting IB. So if your IB value, they are asking to find out, third case, IB is equal to IC by beta. What about the IC? You got 5.65 by beta is 100. That value is a 56.5 microampere. That's why it is a microampere compared to milli. We are neglecting while you are calculating VCE. At the last one, beta factor, beta sensitivity. 1 divided by, I gave the formula to you. 1 divided by 1 plus beta into RL by RB. So 1 plus beta, that is 100, RL is a 1K divided by RB is a 100K, that will be 0.5. So this is about the solution for common base bias with emitter feedback circuit. Next we are moving to the base bias with collector emitter feedback circuit. Base bias with collector emitter. Okay. Here base bias with collector emitter circuit. Just what is the difference here? Emitter resistance is added. Previously only RL and RB is there. Now you are added emitter. That's why both base bias with collector and emitter feedback. So again the formulas will be, IC saturation is equal to, how to find out the IC saturation? Whenever the IC saturation VC is equal to 0, both are shorted. RL plus RE. So VCC is equal to RL plus RE. Clear? That is the saturation. Next, coming to the IC, now I am going to apply the beta rule directly. I will tell you IC value. Okay? Because already I gave so many explanation for previous two topics. That's why beta rule can directly apply. IC is equal to VCC minus the base into emitter voltage VBE divided by, emitter resistance is RE plus, okay, and then RL plus, this beta resistance referred to collector side, that value RB divided by beta. So this is about the formula for IC. Coming to the VCC is equal to VCE is equal to VCC minus IC into RL plus RE. So that is about the VCE. After that, another formula, K beta is equal to 1 by 1 plus beta into RE plus RL divided by RB. This is the formula for K beta. So finally, that these are the basics related to the formulas related to the base bias with collector emitter feedback. So we will discuss one problem based on that. Then we are moving to the voltage divider bias. In the circuit shown in the figure, find the IC sat. So how to find out the IC saturation? VCC divided by, that is a 15 VCC divided by RL plus RE plus beta into RB. Just now I gave the formula. So 10K plus 500K by beta. Beta is given 100. So it will get the value 0.75 milliamperes. Okay. Next, second bit, IC is equal to actual IC. So I'm sorry, this is not IC sat, this is IC. Okay, this is the B bit. IC saturation we'll see now. This value is 0.6 milliamperes. Now we'll see IC saturation. IC saturation only these two resistors. Okay, so that will be 15 divided by 10K plus 10K. That will be equivalent to 0.75 milliamperes. You got IC sat as well as IC also. Next one, K beta. No, VC you want. VCE is equal to 15, that is a VCC minus IC, that is a 0.6 into RL plus, that is a 10K plus 10K, RL plus RE. So that will be equivalent to 3 volt. So finally K beta is equal to 1 divided by 1 plus beta into 100 into RL plus RE, 10K plus 10K divided by RB is a 500K. That value equivalent to 0.2. So that is about K beta. K beta, another formula, previously what I mentioned, 1 minus IC sat divided by IC sat. You can use that formula also. You will get the same thing. Just verify that. In case of examination, you forgot about this particular formula, we can use that. 1 minus IC sat, IC, that is 0.6, IC sat 0.75, you will get 0.2. Okay, this is a formula 1 minus IC by IC sat. You can also remember this particular formula is applicable for all 4 biasing techniques. Okay, Next, voltage divider bias. So this is the last topic, voltage divider bias. Here voltage divider bias circuit, just two resistors connected across the this particular transistor based across the collector as well as base terminal and emitter. We are connected across the emitter terminal R2 across the collector, and in between the base and the emitter terminal collector terminal R1 is connected. So voltage is divided. So that's why it is called as voltage divider bias. So how it is to calculate this particular biasing technique, we'll see. So now your voltage, now we are focusing about the this particular voltage V2. Apply the voltage division rule. V2 is equal to total voltage, that is a VCC into R2, same resistance, divided by R1 plus R2. This V2 is nothing but a VTH, Thevenin's voltage. In the same case, Thevenin's resistance also connected. Total entire circuit is converted into Thevenin's circuit, Thevenin's equivalent. So RTH is equal to both are R1 and R2 both are parallel. If you are consider in between these two terminals, we are look at so R1 into R2 by R1 plus R2. That means that total entire this particular combination is converted into what? Thevenin's equivalent. This is a circuit. VBB, that is a VTH. This is the formula. And RB, this is a RB, base resistance. So total entire complicated circuit into simplified circuit. Once you this particular combination is there, you can directly do the solutions. Okay. So now we are moving to emitter voltage. You want emitter voltage is equal to V2 minus VB. How it is V2 minus VB? This particular voltage, this particular V2 present across here, in this case present across here, V2 minus VB is equal to RA, VE. That's what here formula. Next, IE is equal to VE divided by RE. Okay. What is the VE? V2 minus VB divided by RE. If your VBE neglected, so once VB neglected, V2 divided by RE. That is a formula for IE. Next, VC. That is nothing but a VCC minus IC into RL. That is a general formula. VCE is equal to VC minus VE. That is a VCC minus ICRL minus VE is nothing but IERE. That value will be equivalent to VCC minus IC into RL plus RE. You know that IC saturation is equal to VCC divided by RE plus RL plus RE. Because we discussed, IC saturation, both are, shorted RL plus RE, VCC, the same thing. That's why I'm not spent so much of time here. So finally, KB value is equal to, K beta is equal to 1 divided by 1 plus beta into RE divided by R1 parallel with R2. This is about the K beta. Clear? We'll see this particular problem, voltage divider bias case. So what they are asking, for the circuit shown in the figure, find the IC sat, IC and VC and K beta. So VB is neglected, beta is a 500. Okay, so first point, IC saturation is equal to VCC divided by, these two are shorted whenever saturation 2K plus 6K, that is a RL plus RE. So 20 divided by RL is a 2K and RE is a 6K. That will be equivalent to 2.5 milliamperes. Okay. Next, B bit. In the B bit, IC is equal to, so second one is IC is approximately equal to IE. That is a V2 by RE. Just now I gave the formula. Whenever you are converting to Thevenin's voltage, V2. So V2 is equal to, how to find out the V2? V2 is equal to Thevenin's voltage, total VCC into R2, that is a 6k divided by total resistance 6k plus 20k, that will be equivalent to 26 volt, that is a V2, using voltage divider concept. So just I will use directly 6 divided by RE is a 6k, that will be equivalent to 1 milliamperes. Okay, fine. Next, third point, C is a VCE is equal to VCC minus IC into RL plus RE. Okay, these two combination. So VCC is a 20 minus IC is a 1 milliamperes, RL 2k plus 6k, that will be equivalent to 12 volt. Finally, D. These two are connected parallelly. So R1 parallel with R2, that is a 80. What is R1 value? R1 value 14 and 6. So 14 parallel with 6k, that will be equivalent to 4.2k ohms. So finally KB, you want KB factor. KB is equal to 1 divided by 1 plus beta. Beta is a 50 into, parallel combination. What is a parallel what is a RB? RE 6 divided by parallel combination, 4.2, that will be equal to 0.0138. K beta, okay, this is the formula for K beta. Beta into RE by R1 and R2 parallel combination. So finally, that is about the solution. Okay, so I hope that everyone is enjoy the class. This is about the load line concept. Okay, now very small topics are there. So DC line, load line and output characteristics. In this particular case, what we discussed in the previously, we are load line in between IC saturation and VC cutoff region. So in between, we are going to select once you calculated, we are going to select the Q point. In that particular Q point, we are going to draw the IB current, we are going to draw the IC current, we are going to draw the output voltage. So all these three combinations we are going to provide it with the help of this particular thing. This particular working we are going to discuss in the next chapter, equivalent circuit, unit 4 first chapter, single stage amplifier circuit cases. Okay, next we are AC and DC load line. They are also very simple. In the case of AC load line, this is a slope we got because your AC resistance included. In case of DC load line, AC resistance is not there, only DC resistance you consider. That's why this is a slope. Okay, so in that case, AC and DC load line equations, just I will provide it to you. In case of IC for DC circuit, VCC by RL. In case of AC circuit, IC is equal to VCC divided by RAC. That is, the resistance is different. So remaining, what are the formulas we applied for before DC load line discussion? All the formulas are applicable here. Don't go much into that. It is enough for the examination point of view. Then we completed the DC load line chapter completely, and then thank you.